This is a British pendulum tester. We start with leveling the arm of the British pendulum tester and ensure the bubble is at the center. Firstly, we need to calibrate the tester. Before we begin with our test, ensure the needle reaches 0 first. Use the ruler to adjust the height level of the arm so it touches 3 points. We start with taking the reading of the British pendulum tester for 3 times on smooth and dry surface. And for wet surface, we pour water on the smooth surface before starting our test. We calibrate the British pendulum tester first so it touches 3 points. Release the slide rubber and take 3 readings on smooth and wet surface. Repeat the same step as in the smooth surface for the rough surface. Calibrate first and take 3 readings on rough and dry surface. Then pour water on the rough surface and proceed to take 3 readings on rough and wet surface.
The objective of this skin resistance test is to measure the skin resistance of different surface types. In this experiment, both smooth and rough surface were tested to understand how surface texture affects the skin resistance. Next, the test aimed to compare the skin resistance performance of smooth and rough surface under 2 conditions, which are dry and wet. This comparison helped to identify which surface provides better friction and is safe for use. Finally, the test is conducted to evaluate the effect of water on skin resistance performance by comparing the result between dry and wet conditions. The influence of water in reducing friction and increasing the risk of skidding can be clearly observed. This test helped to improve understanding of the importance of surface texture and condition ensuring road safety. By the skid resistance test, 4 surface conditions were tested, which are smooth dry, smooth wet, rough dry and rough wet. Based on the result, the smooth test surface recorded an average skid resistance value of about 13.33, while the smooth wet surface showed a further reduction to around 4.33. This value indicates very low skid resistance, especially under wet condition. In contrast, the rough dry surface recorded a very high average skid resistance value of approximately 121.33, which is significantly higher than the smooth surface. When the rough surface was tested under wet condition, the skid resistance decreased to about 74.33, but still remain relatively high. Overall, the results show that rough surface consistently produce higher skid resistance value than smooth surface under both dry and wet condition. From the discussion, it is clear that surface texture has a major influence on skid resistance performance. Rough surface provide higher friction due to better surface texture, which increase resistance to sliding. When the surface condition change from dry to wet, skid resistance value decrease for both surface types. It is due to presence of water, which reduce friction by forming a thin layer between the surface and the test slider. However, the reduction was much more significant for smooth surface, making it extremely slippery under wet condition. On the other hand, the rough surface still maintained a high skid resistance value even when wet, which is considered safe according to skid resistance standard. Therefore, rough surfaces are much safer compared to smooth surface, especially in wet condition, highlighting the importance of surface texture in road safety design.
So these are apparatus used in this test. First, make sure the surface is clean by using a brush, and ensure the surface is about 5.5 cm times 5.5 cm. Pour 25 ml of sand into the measuring cylinder by using funnel. Then, pour the sand onto the clean surface and disperse the sand in circular motion by using surface rubber. And lastly, measure the length of the sand to obtain the diameter of the dispersed sand. Take 3 readings for average data. For rough surface, we repeat the same step by starting off with cleaning the surface. Use funnel to pour sand on the measuring cylinder until it is 25 ml. Pour the sand onto the clean rough surface. And disperse the sand with rubber in circular motion. We then measure the diameter of the sand by taking the average data for 3 times.
Sand patch test. Firstly, objective. Objective number 1 is to measure the macro texture depth of a certain pavement surface. And objective number 2 is to determine uniformity of a surface texture and its impact on tire pavement interaction. Next is result and data. So for the location rough surface, we use volume of sand 25 cm3 and the diameter is 17 cm, 16.5 cm and 15 cm, and the average reading is 16.17 cm. For the smooth surface, we use volume of sand 25 cm3 and the diameter is 22 cm, 20.5 cm, 21.4 cm, and average reading from the 3 tests is 21.3 cm. Next, calculation of rough surface. So the average diameter we take is 16.17 cm, which is 0.1617 meter. We put it inside mean texture depth MTD calculation, which is 4V over MD square, and the result we got is 0.00122 meter or 1.22 millimeter. And then we compare it with 0.5 millimeter. So for rough surface, we got 1.22 millimeter bigger than 0.5, which is the requirement. Next, calculation of smooth surface. So we take the average diameter 21.3 cm, which is 0.213 meter. We put inside MTD calculation and we get 0.0007 meter, which is 0.7 millimeter. And then we compare it with the minimum requirement, which is 0.5 millimeter. So 0.7 millimeter is bigger than 0.5 millimeter. So it meets the minimum requirement. Lastly is discussion for the sand patch test. So for the rough surface, MTD we got 1.22 mm, which exceeds the minimum requirement of 0.5 mm. So it shows the texture is deep and correlates with the strong skid resistance. For the smooth surface, we get the MTD 0.7 mm. It exceeds minimum standard, but it's lower than rough surface. So the texture is fairly deep, correlates to poor skid resistance in dry and wet condition. And the rough surface gives better performance than smooth surface due to higher texture depth. However, both surface meet basic texture requirement.
Firstly, starting with cleaning the surface and place the outflow meter onto the clean surface. We then ensure the level is closed before pouring water into the outflow meter. Pour water into the outflow meter until it reaches 200 ml. We use stopwatch to measure the time taken, release the level and immediately start the stopwatch. Wait until it drains out. Close the lever and stop the stopwatch. We repeat the same step but on a rough surface. After the lever is closed, start pouring water into the outflow meter until 200 ml. Release the lever and start the stopwatch and wait until it drains out. Take 3 data for average and for accuracy.
Objective for surface drainage test. First, to analyze the pavement efficiency in draining surface water. Second, to identify areas prone to water pooling which may leak hydroplaning or pavement deterioration. The surface drainage test result clearly demonstrate the influence of pavement texture on permeability. Using feet of 200 ml, the road surface exhibit the most efficient drainage capacity with the shortest average time of 5.54 seconds and the highest rate of flow at 36.1 mm per second. Conversely, the smooth surface impairs that water flow recording the longest average time of 8.34 seconds and the lower flow rate at 23.98 mm per second. The median road surface fell between this value. Thus, trend indicated that increased microtexture depth significantly enhanced the pavement ability to dissipate water, which is a critical safety factor for minimizing hydroplaning during wet conditions. Conclusion: road surface. Road surface provide excellent skid resistance and effective drainage, meeting or exceeding the requirement of Malaysia standard. Median road surface. Median road surface are generally acceptable. However, their performance is marginal with potential safety concern under wet condition. Smooth surface fail to meet the required standard for skid resistance and texture depth, particularly during wet weather, which may pose safety risk. Safety recommendation: to improve road safety, it is recommended that road surface maintain adequate texture depth and skid resistance in compliance with all existing relevant standard.